Welcome to this video on titration. We're going to look in this video at trying to understand what is going on in a titration at the submicroscopic level. We've got two learning objectives. We want to try and understand the purpose of a titration, and secondly we want to try and understand how the endpoint of a titration can be used to infer the amounts of the reactants present. So what is a titration firstly? A titration is an incredibly accurate technique to work out how much of a substance is present. And in chemistry terms, if we're talking about the amount of substance, we're talking here about the number of moles. So there are basically three stages to the titration technique. The first is to prepare a solution of your sample. The second, you react that with an exact quantity of another substance, and that's where the idea of indicators comes in, because the indicator indicates when you have the exact quantity of the other sample. And then you're going to use the reaction equation, as we'll see in future videos, to work out the amount or the number of moles present in your sample. And the power of that is that once you've got the number of moles, you can use that to calculate concentration, you can use that to calculate mass, you can use that to calculate a whole manner of other related properties that allow you to access things like the percentage purity, the formula of a compound, and so on and so forth. So that's the basic procedure. Let's think about what's actually happening at the submicroscopic level in a titration. So here we have a sample, a very typical titration involving hydrochloric acid reacting with sodium hydroxide, and that's producing water and sodium chloride. And what this equation actually tells us, for our present purposes, is that one molecule of HCl, or equivalently 1 mole of HCl, will react with 1 mole, because that's the balancing number here, we just don't write the ones in. 1 mole of HCl reacts with 1 mole of NaOH. And when that happens, you produce 1 mole of water and also 1 mole of this salt, NaCl. It doesn't tell us about masses, it doesn't even necessarily tell us about reacting volumes, but it does tell us about moles, because the mole is directly proportional, the number of moles is directly proportional to the number of particles, and the equation tells us that every time you have 1 HCl, there's always going to be 1 NaOH reacting with it. Now, if you know about ionic equations, the ionic equation is just really telling us what's actually going on, and it turns out the chloride ion and the sodium ion here are just spectator ions. And actually what's going on is that we have 1 H plus ion reacting with 1 OH minus ion to make 1 mole, or 1 H2O, and equivalently they could be numbers or moles. So I just want to think about what's going on in our titration as we go through. And when we do a titration, we start off with, say, in a conical flask, some alkali, and I'm imagining that I have 1 mole of hydroxide, of sodium hydroxide, and I've represented just the hydroxide ions here because they're the only ones going to be involved in the reaction. So at the start of our titration, so this is the beginning of our titration, we have, so this would be the start of our titration here. At the start of our titration, we've got lots of alkali and currently no acid, so the pH of this is going to be pretty high, maybe around about pH 13. Now in the titration we would then perhaps have, so if this was in the conical flask, and this would be added from a device called a burette. So the HCl is added from the burette. At the start there's none that's been added, and some way later we're going to imagine that we've added less than a mole of HCl. So I imagine that I'm putting some H plus ions into here, like that. Well, the reaction ionic equation tells us that the H plus will react with the OH minus in a 1-to-1 ratio and actually produce some H2O. It's going to do the same here as well. So some while later, after I've added a little bit of acid, I've now got a lower concentration of OH minus, and so my pH is going to have dropped. Now how far is it going to drop? Well, I've still got an excess of OH minus, so it's going to be somewhere bigger than 7, but less than 13. It's going to be alkaline in pH. So this is some acid added. Now imagine I get to a stage when I've added exactly 1 mole of NaOH and 1 mole of HCl. Well, if that's the case, I'm going to have the same number, if this is constant volume, of H plus as OH minus ions. And what that's going to mean is that all of those are going to react to make water. Now at that point there, with this combination of acid and base at least, the pH should be exactly 7, it should be neutral. There's no excess of OH minus or H plus ions. Now, then, if I were to keep on going adding this, and I add an excess of hydrochloric acid, then I would end up having removed all my OH minus ions. Get rid of all of them. They've all become water. But now, if I kept on adding my H plus ions, I would now start to get excess acid, like so. And my pH would become less than 7. So how does this actually relate to titrations? Well, if it's possible to determine via the use of an indicator when we have a neutral solution, then it's possible to use that information to infer that exact quantities of HCl and NaOH have reacted according to this equation. Let me try and explain that again. So let's say that this is the end point of our titration. This is when the indicator changes colour. If we have an indicator that changes colour at exactly pH 7, then we know that if we started with 1 mole of NaOH, we must have added exactly 1 mole of HCl, because the reaction equation tells me that 1 mole of NaOH reacts exactly with 1 mole of HCl. And that's how titrations can be used. If we start off with a known quantity of one or other of these two, once the indicator changes colour, we know we must have added the right number of moles indicated by the stoichiometric or the mole ratio in the equation. So that's why this technique is so powerful. If we prepare a solution of the sample and we add the exact quantity of another substance, we can then use the reaction equation to work out the amount present in our sample, and from that we've got many, many options.